So this video introduces the algebraic limit theorem, which technically we already saw in our Zoom activity the other day. So this theorem is abbreviated ALT, and it just tells us about what happens when you put convergent sequences together arithmetically. What can you expect happens with their limits? So it is important to note here that we are making the assumption that AN and BN are convergent sequences. If they are not convergent, then we don't necessarily get the conclusion of the ALT. It could be in some cases that divergent sequences produce convergent arithmetically composed sequences, but it's not guaranteed. In some cases it's not. It doesn't work. So we took a look at the ALT part 1, and I am going to prove that in this video, rather than posting the solution for it directly on the Zoom activity. But one other thing I want to point out here is the fourth statement about the quotient of two sequences. So notice that we say that this converges to A over B provided that B is not 0. Some people will ask what happens if Bn is 0. If you're going to talk about a sequence, by definition, it is a list of real numbers. And so if talking about the quotient sequence An over Bn even makes sense, then we are implicitly assuming that Bn is not 0. Otherwise, that wouldn't even be a sequence. It wouldn't be a list of real numbers. And we're assuming this for all values in our sequence. Okay, so let's take a look at ALT part 1. So our goal is to show that CAN converges to CA. So if I was doing this problem on my own, I would start by writing out the definition of what I am trying to show. So that definition says I need to show for all epsilon greater than 0, there is a capital N in the natural numbers, such that for all n greater than or equal to capital N, I need the absolute value of CAN minus CA to be less than epsilon. So when I'm thinking through this proof, my whole goal is to figure out how do I choose the tail of my sequence so that I meet this error constraint. Now, so if I was just focusing on high level, I would say I want to figure out how to make CAN minus CA less than epsilon. And then I would ask, well, what expressions do I have control over the size of? Well, according to our definition of, or our assumption that AN converges, because remember that is a key part of the ALT, it's a global assumption that we're making for all 4 parts of the ALT. That tells me that I can choose a tail such that AN minus A is less than anything I want. And I'm putting a box here, and the box is just a placeholder for any positive real number. I'm avoiding reusing epsilon here because it may be that the tail that we need to choose for the sequence AN is actually in a different sized band than epsilon. We saw in our example in class that when we were looking at twice AN, what we needed to choose AN's tail for was the epsilon over 2 band instead. So the way I want to think through this is I should be asking myself, how does the expression I want to show is small, which is CAN minus CA, depend on the expression an minus a that I know I can control the size of. So this is just giving us an idea about how we might want to arithmetically manipulate our expression to get what we want. So I would take CAN minus CA, I would factor out the C. My goal is to isolate AN minus A by itself so that I can see exactly how the size of CAN minus CA depends on AN minus A. Now when I pull this apart and I split across absolute values, I must apply absolute values to both of my terms here. So I do have an absolute value C when I pull things out. Now, I know this is less than the absolute value of C times whatever box I have decided is going to be the size of AN minus A. So my goal is such that when I plug something into that box, I want epsilon to come out because that was what I was saying I needed. So it appears that what I should choose for my box is epsilon over absolute value C. If you are going to choose that to be your box, remember the constraint that our box has to be a positive real number. It should be a fixed positive real number. And as long as it meets that constraint, then I can choose a tail for AN that will result in AN minus A being less than whatever I put in my box. So the one thing that I need to make sure I have answered is epsilon over absolute value C a positive real number? And if it's not, then I can't do this. Well, remember in part 1, we are saying that this is any C in R. And so in particular, I need to worry about what happens when C is equal to 0. If C is non-zero, then this will be a positive real number because I've incorporated absolute values in the expression to handle the case when C is negative. So we have to ask the question, what if C equals 0? Because we cannot use epsilon over absolute value C in that case. So when you have a case like this arise, what you do is you go back to the original question. Remember what we were trying to prove. We were trying to prove that if AN converges to A, then CAN converges to CA. That's what we were trying to show. But if C is specifically 0, notice that CAN is just the sequence 0, 0, 0. And that's the constant sequence, which means that sequence is always in your epsilon band, regardless of which term you're looking at in the sequence, because it remains constant. So this converges to 0, and that's really 0 times A. So this case is sort of trivial, but we still need to make sure that when we write up our proof, we have handled things correctly. So let's go ahead and write the proof. So this is proof of ALT, part 1. So what we are proving here, there's also this for all C part right here in front. So overall I have an implication, which means my overarching structure, logical structure of my proof should be assume the hypothesis and show the conclusion holds. So I am going to assume AN converges to A, and then my goal is to show that for any C that I pick in the reals, CAN converges to CA. So the format of the conclusion is now going to tell me how do I, oops, did not mean to do that. How do I continue in my proof and lay out the logical structure of what remains. So I have to prove for all C, which means I need to let C be in R. This is just an arbitrary value. Now remember, the value of C determines how I am going to prove this. When c is 0, I have to do something else. So that means we're at the place where we're ready to split into cases. So case 1. Here, I'll write this as c equals 0. Well, then in this case, CAN is just the sequence 0, 0, 0. We know that's a constant sequence. It converges to 0, and that is C times A. So this case is true. Done. Now, case 2 is when C is not 0. So now we need to figure out what to write for the case when C is not 0. When we go back up, we need to remind ourselves what we're trying to do here. We're trying to prove that CAN converges to CA, which is this boxed statement. And that says to do that, I need to introduce an arbitrary epsilon. So I need to let epsilon be greater than 0. Now, I must find the next thing in my list, so I've done that. The next thing I need to do is find my capital N, and we said the way we get the capital N is by referencing the definition of AN converging to A, but specifically using the value of epsilon over absolute value C. So we can note here epsilon over absolute value C is greater than 0 since C is not 0. This is a real number. So because AN converges to A, there has to exist a capital N in the natural numbers such that for all little n greater than or equal to capital N, the absolute value of AN minus A is less than epsilon over absolute value C. So right now, I have successfully introduced the existence part. I've introduced my capital N. I need to now demonstrate that for all little n in that tail, CAN minus CA is less than epsilon. So then we can say for all n greater than or equal to capital N, if I look at CAN minus CA, that's really the absolute value of C times the absolute value of AN minus A, which is less than the absolute value of C times epsilon over C, absolute C. I'm just using my hypothesis here about my tail for AN, and that's epsilon. And so, in either case, CAN converges to CA. And we're done. So the last thing I'm going to demonstrate in this video is how to prove the algebraic limit theorem part 2. This is going to illustrate a very common type of argument that we need to be able to do. So let's take a look at it. So we're looking at ALT part 2. And we want to prove if AN converges to A and BN converges to B, then the sum of those sequences, and this sum is being done term by term, should converge to A plus B. Again, when I am proving a claim, I want to be focused on the conclusion. The conclusion is going to tell me the logical structure for how I need to approach this problem. So the first thing I would do is write down the definition. We want to show for all epsilon greater than 0, there exists a capital N in the natural numbers such that for all little n greater than or equal to capital N, we're taking the absolute value of AN plus BN and subtracting A plus B. And we want that to be less than epsilon. So just as we did in the proof of ALT part 1, we want to focus on the expression that we are trying to make small. So we want an plus bn minus a plus b to be less than epsilon. So we want to focus on what does that mean about, how can I figure out how this depends on other expressions that I do know can be controlled and made small. So writing this down, we want an plus bn minus a plus b to be less than epsilon. And we know that an and bn converge, and their convergence expressions are going to give us control over making an minus a less than something, and then bn minus b it can also be made small. And I'm going to use a triangle here because I don't know whether or not I want to choose the same band for an minus a as I do bn minus b. As long as I have a fixed positive real number, I can choose tails for an and for bn that meet these constraints. So again, I'm asking the question, how does the expression I want to show as small depend on the expressions that I do know are small? So my goal is to take an plus bn minus a plus b and manipulate this algebraically so that I can see an minus a isolated by itself and bn minus b. So the first step, I can distribute this subtraction and rearrange my terms. This is really an minus a plus bn minus b. So now I've isolated those expressions, but notice that I need absolute values around both of them before I can make any type of substitution, which tells me I need to split these absolute values across the addition. Now when I do that, I'm using the triangle inequality. So I get an minus a plus, so in absolute value, plus the absolute value of bn minus b. And now I want to figure out, here I'll make this bigger. I want to figure out what should go in my box and what should go in my triangle. So here's my box, and then here's my triangle, what should go in it. Well, the way we choose what goes in it should be such that when we add these together, epsilon comes out. Well, there are all kinds of choices we can make here, but probably the most natural choice to make would be let's put epsilon over 2 in both of these boxes. But I could have done like 3 epsilon over 4 and 1 epsilon over 4. So you have some choices here. So this tells me that I need to choose the tail for epsilon over 2 for both of these sequences. Now, when I go to choose an and bn, they probably don't have the same tail, that chopping place, like the same capital N that puts an in epsilon over 2. It doesn't necessarily have to be the same capital N that puts bn in the epsilon over 2 neighborhood. So this is, we're going to get N1 that does this. And then we're going to get a different tail N2 for Bn. And then we need to make sure that both constraints are met. We need to be both in the tail of An and in the tail of Bn. And the way we can guarantee that is to use the max value of this. Use n to be the max of n1 and n2. Because I know that if, for example, when Bn is in the tail according to n1, if that's not in the epsilon over 2 neighborhood, it's because I needed to go further down and n2 was actually larger. So as long as we are past both n1 and n2, then we can use both of these sequence constraints. Let's go ahead and write this up. And actually, before I write it up, let's just draw a quick picture for those of you who may not be tracking what I'm talking about here. So I'm going to say I've got two sequences that are going to do something. I'll say that this is my sequence AN, and it looks like it's converging to A. And then I've got some other sequence BN, and it's doing something. I don't know what exactly it's doing. Maybe it's going down here, but then ultimately converging to B. So this would be B. Now, if I was drawing an epsilon over 2 band, I could say, okay, let's make this my epsilon over 2 band. But when I go to do the epsilon over 2 band, I'm putting it in different places depending upon whether or not I'm talking about convergence around A or convergence around B. So here's my band down here. Notice that if I wanted to make sure that my tail for AN is in this band, then I can use I can use capital N equal to 3. So this is kind of like my N1. But notice that if I use capital N1 equal to 3, B is not in its epsilon band yet. And so when I go to do that, I actually need to choose N2 a little bit bigger. So as long as I'm past both N1 and N2, then both sequences will live in the appropriate tail. And that happens when you choose the maximum of N1 and N2. All right, let's write out the proof. So remember what we're doing again. We're proving an implication, and so we need to make our assumption that AN converges to A and BN converges to B. Now what we do from here is dictated by the definition of the conclusion that we're trying to show. So I go back up and I want to be focused on this definition. I want to introduce an arbitrary epsilon and then explain how to get the tail so that my sum sequence is in the epsilon band. So let epsilon be greater than 0. Now it's time to find capital N. But remember, to find capital N, I need capital N1 and capital N2. So I'm going to go ahead and use my definitions of convergence, AN minus A and BN minus B. So note here, first of all, epsilon over 2 is a positive real number, which means we can use the definition of convergence on this value. So because AN converges to A, there has to exist an N1 in the natural numbers such that for all little n greater than or equal to capital N1, AN minus A is less than epsilon over 2. And similarly, I can do the same thing because BN converges to B. There has to exist an N2 in the natural numbers such that for all n greater than or equal to N2, AN minus A, or sorry, BN minus B is less than epsilon over 2. Now we're not done introducing our tail for the sum sequence. Right now we've only introduced tails for AN and BN. So now we need to say let capital N equal the max of N1 and N2. And again, we're doing this so that we can use both constraints simultaneously. So then for all n greater than or equal to n, I can start taking a look at my computation, AN plus BN minus A plus B. We know that that is less than or equal to AN minus A plus BN minus B, just using the triangle inequality here after rearranging. And then that's less than epsilon over 2 plus epsilon over 2, which is epsilon. And that's exactly what we want to show. One thing here, this is because n greater than or equal to n implies little n is greater than or equal to n1. And then I can use the second condition because n greater than or equal to capital N implies that little n is greater than or equal to n2. So by definition, an plus bn as a sequence converges to a plus b. So what this proof is illustrating is that sometimes we might have two sequences in play, and we need both of those sequences to each meet some kind of constraint. And the way we do that is we choose the separate tails that we're allowed to get for each sequence based on the definition, and then we pick capital N to be the max of those two tails so that we can guarantee that being in the tail associated with capital N means you are transitively in the tail for N1 and the tail for N2 for the corresponding sequences. And that's it. There's just one more thing that I want to point out about the algebraic limit theorem, and that's that the converse of this theorem need not be true. And so when I say converse, what I mean is I can write out each of these statements as an if-then statement. I can say if AN converges to A, then CAN converges to CA. Just because CAN converges to CA doesn't mean AN converges to A. Imagine C was 0, for example. That might kill off some kind of oscillation behavior that's being hidden inside AN. So the converse of the ALT need not be true. If a sum sequence converges, that doesn't mean that the individual sequences have to converge. They could both have divergent behavior that's sort of equal and opposite and cancels each other out when you add them together. So the converse of the ALT need not be true. And again, my other warning is that if you're going to use the ALT, you must know that the sequences you're working with converge.